Right. So can we start, Dr. Safa, or?
Let's wait 1 minute.
Okay.
Just 1 minute.
I think most of you have some issues regarding downloading Lumerical. I mean here regarding the Photonics team. I mean Dr. Muhammad Waqqar and Marianka. I think. Or
Yeah.
yes, Marianka, how are you?
I'm good. What about you, sir?
Great, thank you. So, do you have any issues regarding downloading Lumerical package?
I'm using a Linux. Yeah, I'm using a Linux system, and I downloaded the setup file or maybe the zip file. I don't know how to extract it and install it. Thing is.
So great. I will send you the link in the chat. So I believe that you do that before. So you go for evaluate this for free. I believe that you do that, yes. And you download the great, yes. Did you download the license manager or not?
Yeah.
Who said yeah?
Can you throw up this link in Discord server?
So
okay,
if you have any issues, you can send it directly. Send it me a screenshot and send it directly, because after you downloading the zip file, you can directly install it very easy, and they will send you the license file. Did they send you the license file via your email?
Okay, wait.
They must send you the license file, because after you doing that, you will uploading this license file, and you will have this 1 month. And actually, they will again send you another email if you have any supervision under any institution, startup, or university, and you can extend this 1 month. But first of all, you need to have this license file, So we can do that after this meeting. And I think Dr. Muhammad had the same issue, to download the package. So great, we can start. Cannot attend today, Muhammad. So we record this meeting for him. Actually, I think he's a very valuable team member. He's great. So great. So how are you again? Today we're going to actually technically simulate the photonic crystal fiber. And this actually photonic crystal fiber from this image, if you see that before in the, for example, in our validated papers, you can see the same image for photonic crystal fiber. So the main question is, how can we simulate this photonic crystal fiber using Lumerical, right? So actually, this is a solved example in Lumerical, and I will send you all the links and videos regarding that after the meeting. But first of all, you need to, of course, as we said before, you need to download the Lumerical itself. So actually, I'm trying to use my Mac. So. Great. If you download this file from here, if you can see this file, LMA, and this file is for the solved example of the photonic crystal fiber. But what we are doing right now, what we are about to do, is to create this photonic crystal fiber from scratch. But first of all, why we use the Lumerical mode? As we said before, there's a lot of different packages for Lumerical. One of them, we will use the Lumerical mode for simulate this type of photonic crystal fiber. Why mode? Actually, the simulated solver is FDE, or finite difference eigenmode solver. And actually, there are two different solvers, like for example 2.5, the variation of finite difference time domain, and bidirectional eigenmode solver, example EME, actually expansion. You will find all of them when you download the numerical mode. So, but specifically, we will use finite difference, or actually FDE. Why? Because actually our fabricated or our photonic crystal fiber is uniform. Actually, where the cross section is varying, or such as a taper, for example, if you know the taper before, we will use the var finite difference time domain and email. But we will use, actually, for the photonic crystal fiber, there is no, there is a uniform structure in the z direction. And this direction actually is the light propagation direction. So we will assume that the light will go in the z direction. So there is a uniform, and hence we will use the finite difference time domain, because in the z direction, our structure is uniform. It's not uniform, non-linear. We cannot use finite difference eigenmodes. It's very important. So what we are doing right now, actually, this is our structure, but we will create new file. Yes, that's it. That is actually the GUI after you downloading the numerical package. Actually, from here we will use finite difference eigenmode solver, as we said before. So new project. Okay, don't say it. Yeah. So great. We will what we will do right now is to step by step we will use use the steps from numerical to create this structure. And actually, if you have any question regarding or that, you can put it in the chat. So as he said, begin by starting mode. You can save the mode simulation project as we said before. But first of all, we are trying to add the material. And the material here is very important, because that's actually what we are about to modify or to manipulate regarding our sensor, So for example, we will use Selmayr material. And how can we do that? We will go for the material database, and we will add from here. I hope you see my screen, of course. So when you press add, you can see a lot of models to simulate different materials. As you may know, that any material you can model use different models. For example, if you are about to use graphene, that's a 2D material. You need to add a graphene from here, but we will use a Selmayr equation. And of course, if we can do that, Selmayr equation, you can, for example, see that for example, we have different parameters, and we are about to define these parameters for our design and put different parameters into the numerical package to properly simulate this material. So, for example, we are about to fill these parameters here from what? From here. So, great. Of course, the naming, and we can do that, but A0 is 1 and B1. What you're about to do is actually copy and paste it. And of course, this parameters is different from material to material. That's a great question. So for example, if we ask Dr. Safa to have, she asked us to add different material, for example, for a blood or whatever. We need here to provide us with these parameters, no? CBQ. Of course, sorry for wasting your time, but I need to do that step by step for you, and you can do that by your own, of course, after downloading the numerical. So great. And here we can, of course, as we said before, to add the naming of this material. And of course, again, after Dr. Safa provide us with different material, she need to provide us the name, the different parameters, and all, or of course, the optical parameters for this material, for different materials. And for your information, actually, the materials model is types actually has two types. You know, all of the material regarding to permittivity and conductivity. That's for your information. After we done that, we can add. You can find it here. Yes, there we go. Okay. So again, we are about to add structure, and this structure actually for the fiber itself. And we can, from the structure, add a circle, as they said, and we will name it to be a fiber and fill again the parameters. If you get the idea, we can move on directly to the solid example, but I prefer to do it, to consume some time to do it step by step. So we will name it to fiber, and x0, y0, and z0, and actually z minimum and maximum is regarding, actually the data span is about 1 micro, negative 0.5 to positive 0.5. So we can set that, and actually this is the z direction that we assume that is a uniform in this direction. So this direction is how where the light go, where the light propagate. Actually, it's propagate in the z direction. That's why we use again finite difference eigenmodes, right? And we will change the material, you know, to what we added right now. If the material is appeared in this list here, so we add it properly, you know. If it doesn't appear, actually you need to modify to go again to the material database to add it correct, right? So yes, the radius. We miss the radius. Right. Actually, the radius is about what? Because it's very important, is 300 micrometer, you know, because we can set the micrometer as, if any one of you used COMSOL before, you can set this micrometer to nanometer, whatever, from the very beginning to be validated to all of your measurements. So 300 here, you can do that. Actually, that's the radius for what? For our circle, for our fiber, you know. So now we are about to add the photonic crystal itself. So how can we do that? We will go to the components, and this is photonic crystal. On the left, on the right side, actually, you can see different structures of the photonic crystal. You know, that's different structure. It depends on what you are about to design. You know? So here in this design, we are about to use edge cavity, and edge cavity is why the naming of that. You can of course read the description from here, and we will add those photonic crystal in this structure. Of course, as we said, you can use different structure and different parameters regarding this photonic crystal, and you can add new. Again, you can do that because photonic crystal actually is regarding you are about to create a cavity, but you can use you can create a waveguide or depend on your design, you know, depend on your device that you're about to use. So we will edit the object the same, and here of course we need all of them to be in the origin, and so we can of course by default can use this in the origin and to be in the spot. Again, 0, 0, 0. The material here is H. What's the meaning of H? H is non-material. There is no material, air, you know. So if you can dig into your design, if you need to this specific photonic crystal to be made of only air, you use H material. H, what is the meaning of H? There is no material. Actually, that means that this material is air, you know. So we will use H. We will find it here. Again, the H number, you can guess this H number. We can use different H number right now. So H number 1 is this band 1. And if you read the paper that Dr. Safa provide us, you can specify this specific parameters from the paper that you are about to validate. You know, so different parameters, different design. You are about to put this in this in whatever you are about to change, the radius, the A, the inside, whatever, you know. 5.8. It's very easy actually, you know. So great. So here, if we can change, we forget to change the name. So again, there's always a change to forget the name, but okay. So if you notice that when we set H number to 1, there is a hole here, you know. This hole, this material actually is a material of the fiber itself. So if we change this H number to be 2 or 3, let it 4, okay. So that's the cavity, you know, it's the difference. So we are about to, again, to set 1, 2, 3, 4, 5. So if we set it to 3, all of this photonic crystal will be removed to be the width of the cavity itself, you know. I hope that you noted that. So only what we are about to do is to make it to 1 because we only want photonic crystal to be removed. To be this point is where the light will propagate inside our fiber, you know. So we add our material, we add our structure. It's time to add the simulation region. A simulation region is very important because actually in this region, what we are about to do is to add the simulation region from here. And we, as we said a lot of time, we are about to add the eigenmode silver. And okay, we can let it to the last of it. So great. And the silver type, of course, as you may notice again and again, to D in Z and in Z direction, of course, it's normal. So we are about to change the geometry. Again, X equals 0, Y equals 0, and Z equals 0 because all of that is our design structures are oriented around the origin, the point 0, 0, 0. No? Here, the X span is 12 multiplied by 23.2 because that's regarding our mesh, and we are about to elaborate this in after a very short time, because we need the mesh. Of course, if you have if you know what the definition of mesh, we need it to be uniform again, to have more accurate results, more accurate analysis. We will back to this in a few times. So wise band again. And we will go to the mesh setting to be 60 by 60, and I will elaborate this for you right now. I know the boundary condition. The boundary condition is very important because I know that most of you haven't haven't any background regarding photonics before, so I will provide you with the definition, the glossary of what's the meaning of bi-mesh, what's the meaning of simulation region. But please try to be with the same ground. If you don't understand something or whatever, you can move on and we can back to it. But the boundary condition itself is actually BML because we are about to simulate the photonic crystal field. So if we set it to be PML in X and Y or whatever, we need all of the light to be reflected. You know that? So not all of the light to be absorbed. For example, if we are about to design a solar cell, for example, we cannot set it to be BML, because we need we need to specify the efficiency of the nanowire, for example, the solar cell, for example. So we actually measure the light that we trap into our device. But here is another structure, because we need to design the light to be only reflected, totally reflected in the photonic crystal field. No? So we different boundary conditions again regarding different objectives or different the device. No? So we set all of this to be PML, and actually you can use, for your information, if there is no radiative loss, you should start your simulation using metal. That's for your information. No, not BML. Why? Because actually metal will be faster and more computationally efficient. Maybe your device is more complicated than this. It's actually a very extremely easy design, but maybe your design is more complicated, so your simulation will take more time. So to be computationally efficient, you can use metal. Why? Because actually the BML can create what so-called artificial modes, So actually it's will consume the simulation type. So we will set it to be symmetric. And actually, if it is symmetric in Y, it's regarding to PE modes. If it's symmetric in X, it's about EM modes. And what's the difference between TM modes and PE modes? I promise you, I will provide you all of it, but I cannot elaborate all of this in this very short meeting. But I will provide you with this terminology, of course. So whatever, that's not our point here. So great. So great. What we are about to do, we can answer some question here. Share the link for Dr. Safar. How do we obtain these values? Yes, actually is of course, yeah, I will do that. Definitely, I will do that. Zainab, I think, I believe that I believe is regarding your design. You can what we are about to do after doing all of that is to modify the material, is to modify the structure, is to modify everything. Why? Because we are about to create something else. But the basic structure for all what we are about to do is this. So for example, if we need to use different material, we definitely use different parameters. Sorry.
Can you hear me right now? Can you hear me?
Um,
Can you hear me?
I hope you can hear me right now. Yes. Okay, great. So back to Dr. Zainab question. So again, how do we obtain these values? Is depend on your design. Totally depend on your design. And we will back to this to this question actually because we need to use different materials and different instructions and different everything, you know. So but as I said before, this is the basic for what you are about to change, what we are about to modify, you know. So and after we go to the analysis, the model analysis and the frequency analysis, you might get this intuition why we use different parameters and what concept. Because for your information, Dr. Zainab, we cannot use different structures, parameters arbitrarily. For example, if I am about to change, for example, if I am about to change these circles, you know, these circles to be squared, for example, or whatever, to be anything in your design, you need to have the concept. Why? Because you need to have the equation, the intuition behind it. So again, for example, I was designed a nanowire solar cell, and I created like a star. So my supervisor, Dr. Nella, I remember that she asked me why star, you know. So it's a very important question, because if you are about to publish a paper, and of course the parameters of the star is totally different from the parameter of the circle, only the radius. So, and if you are about to use, for example, particle swarm optimization, you need to define the parameters that you need to be optimal, you know, to efficiently design your sensor or your device or whatever. So that we cannot change the circle to be a square or anything, the material from A to B or whatever, if not we have the intuition or the physical concept behind it. You know, you need to have the answer for all of the modification that you are about to change in your design. I know that this partially answer your question. I believe that your question is more deeper than this. But if we are about to analyze what we can create, I think you can see the big picture for this values. So I can continue with another question before we go to the. No, it's no time. Thank you, Dr. Spot. Thank you. So there is equations to calculate. Yes, definitely yes. Yes, definitely yes. So okay, we can go to model analysis. We get to analyze this photonic crystal. So actually for Lumerical mode is in the back end is defined the light characteristics. For example, if we run this, we will this is the eigen solver analysis, and here is the properties of our light. You know, the wavelength of our light that we are studied is about 1.55 micrometer, and this is the standard, you know, for all of your design. You cannot, we will not use different wavelengths, but actually we will sweep over a range. For example, from 1.4 to about 1.6 to actually maximize or to study the loss of our waveguide, the effective refractive index, and whatever, you know. And we are about to do that right now, actually. So for example, the model analysis here is, as we said, 1.5. The model trial modes is 20. Search and range, why? We can do that. So, yes. So search near, what's the difference between near and in range? Actually, we will do it in range because we need to specify the higher effective index, and we cannot do that from the scratch. We need our simulation to do this for us, and we can pick the higher effective index. And again, if we define different mesh and if we define different simulation region, we can search around this higher effective index. I will show you right now how can we do that. But again, from 1.44 max n to 1.4. Great. So why we mesh the structure? You can put mesh the structure because you need to properly confirm that the calculation is made correctly. If something is abnormal or whatever, you need to here in this graph. If you notice some abnormal before you're doing your simulation, you can go back to the layout and change the parameters that will affect your design, right? So that's why we measure the structure before we simulate. And now we are about to calculate the modes, right? So in the article, they ask you to stop if one mode is appear. But what I am about to do is we can wait, because I need to show you something. How can we choose the effective refractive index? So I know that we have only one and about 2 minutes, but actually we can join again in another meeting if you have time, of course.
Yeah, we can calculate modes and in this
Actually, the simulation actually is calculating the modes for in the range from 1.44 to 1.4, and the n is the effective index, right? Again, I'm really sorry if you don't have the photonic background, you may miss some terminology. You may miss some important terminologies, but so I'm very sorry for doing that. But after the meeting, I will provide you with a glossary. What is the meaning of the important terminologies? For example, the mesh, the simulation region. And regarding the simulation region, actually, in the simulation region, the Lumerical or any other platform or anything is actually simulate or calculate the modes in this simulation region only. So if you have a complicated design, you will have different simulation regions to study different or you may get bigger simulation region or larger simulation region. But actually the width and the parameters of the simulation region is very important. How can you define the width and anything regarding the mesh or whatever? For example, if you can remember, we defined it to be 60 by 60. We are about to change it to be higher, to more accurate results.